Okay, so let's finish up section 3.2. We're going to define some new operations on vectors and new operations on matrices beyond what we've established. Remember, real quick, we think of a given vector. By default, we think of these as column vectors. So when I say let X be an element of Rn, as is done here, then that means that we can't interpret X as an n by 1 matrix. If I want to think of vectors in terms of row vectors, then we'll have to take transposes. And you're going to see a fair amount of transposes in what follows. First definition is a new operation between two vectors. For vectors, X and Rn and Y and Rm define the outer product to be the n by m matrix X, Y transpose. So probably binary operation isn't the right thing to call this. We're taking two vectors and getting a matrix, it seems. Though I could interpret everything as matrices, but the dimensions are not at all consistent between these. But what we're doing is a vector from Rn, let's check the dimensions, would be an n by 1 matrix. Y in Rm means Y transpose would be a 1 by m matrix. So we're taking an n by 1 times a 1 by m. The ones tell us that the matrix product does in fact exist. And those dimensions also tell us that the output matrix will be n by m. Okay, so outer products of vectors are matrices. Inner products were scalars, so there's one difference between inner products and outer products. Inner products were, I want to say commutative. I could interchange the order of operation. Inner product of X with Y was the same as the inner product of Y with X, as long as we're dealing with real scalars, and we are. That won't necessarily be the case here. Here I've got a problem if I interchange the roles of X and Y. If I try to switch things around, I may have problems when M and N are different. Now with inner products, we only considered vectors where M and N were different. We only considered two vectors with the same number of components. But there's somewhat of a difference. We don't have a commutative operation here. If we consider for given X and Rn, X times X transpose, okay, that'd give us an n by n matrix. Let's look at the entries. The ij entry of that matrix would be a sum. Okay, probably some of these sums are just over an index that ranges over 1, given that we're dealing with matrices, one of whose dimensions is 1. But let's just treat it as the ij entry. You're used to computing those as a sum from k equals 1 to n, x sub ik, x sub kj super t. Okay, so I'm taking this to be the kj entry of the transpose of X. My little notation of putting the super t's in to indicate those. It's easier for me to see, at least, when we write it like that. And add this extra step of saying, well, okay, X sub kj super t, that is X sub jk. But this is exactly how you find the ij entry in a matrix product. This shifts things back to simply in terms of the components of X, which is ultimately all we ought to need. Tell you what, let's swap the orders between these two things. Let's write the xjk first and the xik second. And let's take that xik and write it in terms of a transpose. That'd give us x sub ki super t. Interchange the indices. When you put the superscript on there, you know, the transpose stuff. Now this looks like exactly the ji entry of a matrix product. First matrix X, second matrix X transpose. So this is the ji entry of XX transpose, and we just showed the ij entry of XX transpose is the same as the ji entry of XX transpose. In other words, that matrix equals its own transpose. Yeah, it's a symmetric matrix. Okay. Some new terminology. Outside chance you've dealt with this in linear algebra. It's in the linear algebra books probably. The fact you got time to cover this in a sophomore linear algebra class, I've never had time to do it with all this stuff we deal with in terms of vector spaces and matrix operations. But this is a topic from probably sophomore level, though you rarely have the opportunity to get to it in those classes. Take two vectors, x and y, Rn and Rm. What we're going to do is take a matrix A, an n by m matrix, and consider the product x transpose A, y. This is called a bilinear form. So notice it's a 1 by 1 matrix. When x, we take an individual vector x from Rn, A is a square matrix, n by n. If we look at x transpose A, x, this is called a quadratic form. The difference being we had two vectors, maybe of different dimensions in the bilinear form. Here in the quadratic form, we've got a single vector x, and we've dealt with this kind of matrix product. First off, do the matrix products make sense? Let's see. X is a n by 1 matrix. X transpose is a 1 by n matrix. So we take a 1 by n matrix times an n by m matrix. The n's tell you matrix product exists. From that, we'll get out a 1 by m matrix for these first two multiplied together. And then we're going to multiply that by an m by 1 matrix. The m's tell you, yeah, the matrix product exists. And when all the dust settles, we're actually getting from this a 1 by 1 matrix. We'll state here in a minute, we'll commonly treat 1 by 1 matrices as if they're just scalars. And similarly down here, we'll be getting a scalar out for these quadratic forms. Okay, let me reference my favorite linear algebra book, Fraley and Beauregard, latest edition, unfortunately at this stage is 25 years old, from 1995, defines a quadratic form for a vector x and Rn. So thinking of this as having components x1 through x sub n. As a function of the form, got a sum here for both I and j ranging from 1 to n with a constraint that I is less than or equal to j. This is how they define a quadratic form. And what they'll get, we'll get the similar type things, but what they will get then, say when n equals 3, is something of this form. The use of ij's, think of them as scalars and think of the subscripted x's maybe as if they were variables. So think that way. In quadratic form is quite geometrically suggestive. But what we get out of this is, what we'll get out of any of these is products of two of the variables, the x sub I, x sub j's. So when n equals 3, we get an x1 squared, we get an x2 squared, we get an x3 squared, we'll get an x1 times x2, an x1 times x3, and an x2 times x3. So there's the bi in bilinear form. You're getting these, in a sense, these powers of 2, or these products of 2, maybe I should say. Products of 2 of the variables, x1 with itself, x1 with x2, x1 with x3, and so forth. Linear in the sense that we've got coefficients and we're adding them together. So it's a linear combination of those products of 2 deals. We'll produce the same kind of thing that we've got, but we've approached it more hands-on with matrices and vectors and transpositions. What Fraley and Beauregard then show, having defined this, is for every quadratic form, there's a symmetric n by n matrix A such that the quadratic form is given by x transpose AX. In fact, that's one of the exercises in our textbook, exercise 3.3. So this is how we defined it. This is how Fraley and Beauregard have defined it, but what you're getting, you want to be thinking in terms of this kind of thing here. A scalar times a product of pairs of the unknowns. could be the same unknown. So we'll concentrate on quadratic forms of the form X transpose AX, where A is a symmetric matrix, symmetric square matrix. For some applications of this to geometry, such things come out in terms of conic sections if we restrict it to what, n equals 2. When we go to n equals 3, we could get paraboloids, sort of three-dimensional versions of the conic sections. So anyhow, this stuff comes out of that area of geometry. See these notes that are linked here. Some of my stuff from, it's from Fraley and Beauregard. Again, I'd say it's sophomore level, but you never have time to cover that in linear algebra. But this is this ties it in with some more tangible geometric things. I like pictures. Some more properties of matrices. An n by n matrix A is said to be non-negative definite, also commonly called positive semi-definite, if for every vector X in Rn, matrix A was n by n, and symmetric, we have that the quadratic form X transpose AX satisfies the condition that this is greater than or equal to 0. Remember, that's a scalar. So we're maybe thinking of this as X as a vector of numbers when it comes from Rn. Upstairs, I was kind of pushing for X being a vector of variables so I could make some interpretation in terms of conic sections and such. But here, certainly, X comes from Rn, so these are just not real numbers. And when we do this product, we saw that's a 1 by 1 matrix if you keep up with the dimensions. So it makes sense to say that is greater than or equal to 0. We'll denote this with this little curvy greater than or equal to symbol. Don't really have a title for that, so I'll just have to awkwardly refer to it maybe as curvy greater than or equal to. An n by n symmetric matrix is said to be positive definite if for every non-zero vector X in Rn, we have X transpose AX is strictly greater than 0. Regular old greater than or equal to, because we're just comparing real numbers here. This will denote with a curvy strictly greater than 0. So this is shorthand for positive definite. This is shorthand for positive semi-definite, with a semi coming in terms of the or equal to style. When A and B are n by n symmetric matrices, and A minus B is curvy greater than or equal to 0, we'll denote this as A itself is curvy greater than or equal to B. An obvious notation, and we could deal with that in terms of strict inequalities, strict curvy inequalities as well. But remember, these type of things are all coming to you in terms of this positive definite and positive semi-definite stuff. In terms of this X transpose AX, what we're getting in this is the information that for every vector X from Rn, X transpose times A minus B times X, this type of thing with the A replaced with A minus B is greater than or equal to 0 in this case. So definite and positive definite or semi. If we take two vectors from Rn, if we took an inner product, you know what, that inner product is actually X transpose times the identity matrix times Y. Put that identity matrix in there. You go through the computation here. We could write inner products in terms of these type of matrix products. You could also leave that identity matrix out and have inner products written in terms of matrix products. Here's that little caveat I warned you about. Now, technically, inner products are scalars. Sometimes it's even called a scalar product. And on this right-hand side, if we're treating these things as matrices, technically we get a 1 by 1 matrix out. So arguably the settings aren't right. This is a scalar and this is a matrix. But I'm going to quote Gentle from page 69. We will treat a 1 by 1 matrix or a vector with only one element as a scalar. whenever it is convenient to do so. So that's a convenient disclaimer there. So we're not distinguishing between one-by-one matrices and scalars. They're going to arise in computations of this sort. Okay. We're now going to define orthogonal with respect to a matrix. So vectors x and y from Rn are orthogonal with respect to n by n matrix A if x transpose A y equals 0. If A is the identity matrix, this is your usual old-fashioned kind of orthogonality. And under these conditions, we'll say that x and y are A conjugate with respect to A. They're pushing the view from that previous comment to think of, we can think of regular old inner products in terms of these types of matrix products. So we're going to generalize them by replacing that matrix I sub n with the general matrix A. Well, we used inner products to induce a norm, the norm induced by the inner product, where we took a square root of an inner product. So this allows us to define something called the elliptic norm or conjugate norm with respect to a symmetric positive definite matrix A defined as a square root of x transpose AX. Ooh, better not be taking square roots and negatives. It's okay. We have a positive definite matrix. So having a positive definite matrix tells you this x transpose AX stuff will be non-negative. So you're not taking square roots and negatives. This is really a norm. Well, you'll show that in exercise 3.2.c. So this thing is actually, it is a norm. The usual properties of a norm, interactions with scalars in terms of absolute values. Triangle inequality is the tough one. The fact that it's non-negative, the only time you get 0 out is when you put the 0 matrix in. So those properties are to be established to show this actually is a norm. It's called the elliptic norm because the unit ball may not be round under this norm, but instead elliptical. What happens is this matrix A, in some sense, its entries are going to weigh maybe, if you'll let me use the terminology, it might weigh x coordinates differently from the way it weighs y coordinates. Gentle describes this in terms of scaling the units of the axes in an n-dimensional space and anisotropic spaces. I think I like talking about the XY plane. So what we might do in terms of measuring distances here is, I don't know, the X values might carry their usual weight in terms of measuring distances horizontally. And the Y values, I don't know, they might get shrunk by a half or something in terms of how they affect distances measured in this sense, measured with respect to this norm, this sub-A norm thing. So if I were to draw maybe the unit circle in the XY plane, but when I say unit, I mean measure distances like this for some given matrix A, then we might have that circle not being round. It might range from -1 to 1 along the x-axis and only from -0.5 to 0.5 along the y-axis. That's how you measure distances. Those are actually that's a circle of radius 1 if you measure distances in this unusual way. So we've got it, what was it, 2 wide and 1 tall? That's why it's called an elliptic norm. So we get these ellipses out if we make a proper choice of matrix A. In geometry, it's common, well, geometry is about homogeneous spaces. The space is sort of the same at all locations. This will come up in a conversation of curvature. I could have a sphere. A sphere is a homogeneous two-dimensional space because the curvature is the same at all the points. I mean, the space looks the same at all the points. I look at a flat plane, you look at the space, you magnify it, it's just a little, it looks the same no matter where I look at it. It's flat. It has the same curvature at all points on the sphere. But if I get a plane and put mountains on it, or if I get a sphere and put mountains on it, then that changes the curvature, and it's no longer a homogeneous space. Geometry, in a crude sense, deals with homogeneous spaces, spaces that are the same, maybe in terms of curvature, at all points. Isotropic, forget the and, isotropic spaces deal with spaces that are the same in all directions. I actually know this term more from cosmology than from math, but there's something called cosmic topology, and anisotropies pop up in the cosmic microwave background. You'd expect, if you look in one direction of space, to see the same type of thing you see in a different direction of space. An anisotropy might be you look in one direction and you see things of a certain nature, quite vague, and you look in a different direction and they don't have that same nature. The nature of whatever the hell it is we're measuring is dependent on the directions. The cosmic microwave background has hot spots and cold spots on a very, very small scale. And there's famous maps of the cosmic microwave background explorer and some of the newer explorers of the microwave background. And they display these anisotropies, the certain directions where it's a little bit hotter than it is in other directions. It's on a super small scale. There's studies of these anisotropies to determine the global topology of the universe. I've got a bunch of presentations out there posted online of such stuff. It's actually pretty cool and can be made fairly informal and visual. But when you hear isotropic, it's referring to directions. So the idea with my little comment about an R2 looking at a unit circle that's actually elliptical, yes, because there's anisotropies. You measure distances differently along the x-axis, maybe, as you do along the y-axis. And that's what's making circles be elliptic in shape when you measure distances according to some particular norm. Another type of product of matrices, one we won't use very much, called a Hadamard product. It says, suppose A and B are n by n matrices, no same dimensions, no constraints of square. The Hadamard product of those two matrices is the n by n matrix with entries A sub ij times B sub ij. So you're multiplying corresponding entries in those matrices together, and from that creating a matrix of the same size. This is sometimes called array multiplication or element-wise multiplication. Yeah, well, that makes sense because you're multiplying in matrices element-wise and creating a resulting matrix. The identity matrix certainly exists under this type of multiplication of matrices. Take the matrix of all ones. There's your identity matrix. And it's even more straightforward than the way we multiply matrices. Why do we multiply matrices the way we do? Because it turns out to be an awfully convenient way to multiply matrices, as you see when solving, for example, systems of equations. How about inverses under this Hadamard product? Well, that'd be easy enough if we've got non-zero entries. All you got to do, say, to find the inverse of matrix A is take reciprocals of the entries of matrix A, unless you run across a zero. So under Hadamard multiplication, we've got inverses under Hadamard multiplication, if and only if a matrix has all non-zero entries. Of course, I can't invert the zeros. And this is one of the exercises from the Gentle book as well. And that's probably us parting company with Hadamard products. Here's another kind of matrix product called the Chronicler product or the tensor product. Let A be an n by n matrix and B be a p by q matrix. So no constraints on the dimensions. A and B don't have to be the same size, don't have to have any matching dimensions. We're defining this Chronicler product or tensor product. I'll use the terminology probably Chronicler product in here. Chronicler product of A and B is the NP by MQ, so that's the product of the first dimensions by product of the second dimensions. The NP by MQ matrix, A, Chronicler product, B, defined to be this thing here. So what we've done is we've taken all the entries of matrix A and multiplied them onto matrix B, A11 times matrix B. So actually what we're presented with here in these square brackets is a partition matrix. It's partitioned into P by Q blocks, P by Q chunks, P by Q submatrices. Here's the first one, A11 times matrix B. So what I've highlighted here is a P by Q submatrix of the Chronicler product, A, Chronicler product B. All these things represent P by Q submatrices. How many of them are there? Well, how many entries are there in matrix A? N times M. So we've got N times M scalars, each multiplied by a P by Q matrix. How many in total? N times M times P times Q. So it's the product of those four dimensions, which is what we'd get if we counted elements down here. The claim is this matrix is NP by MQ. Now, how many entries does it have? The product of all of those. So what you're getting out for the Chronicler product is this giant matrix of these dimensions. So for big matrices, these are potentially gigantic. The challenge in Chronicler products is relating the entries of a Chronicler product to the entries of the original matrix. What's the IJ entry of this Chronicler product? Well, where is I and J? What we're looking at here is really shorthand notation because this has been presented as a partition matrix. The first row, second row, up through the pth row in this partition matrix, those are associated with A11 and matrix B. When we go to, remember, that matrix B is P by Q. So matrix B has P rows. So the first P rows of this partition matrix involve A11 times the entries of B. Then when we get to P plus 1, it involves A21. When we get to 2P, that'd be the last row associated with this. I'm going through this for a reason. At 2P plus 1, we'd move down to A31 times matrix B. And for the next P rows, we'd be doing A31 and so forth. So multiple of P rows, multiple of P rows, multiple of P rows. How are we doing on columns? Down this first column, this actually represents Q columns, up through Q columns. So we're getting these rows P at a time and these columns Q at a time because of the way the thing is defined. Chronicler product is also called the right direct product or just the direct product. I'll stick with terminology Chronicler product. Okay, a little more hands-on in terms of where is the IJ entry of the Chronicler product? What is it in terms of the entries of matrix A and the entries of matrix B? Okay. If you have any programming experience, the following will go a little more smoothly for you. I'm just trying to use the rounding down function to fiddle around with the indices. Okay. Let's find the ijth entry of the Chronicler product of A and B. So what we need to do is take I and J and break it into pieces. We're going to do so using the greatest integer function, the rounding down function. Does that make sense? Yeah. What I want to do is say, hey, whatever I is it related to this first bunch of rows, this second bunch of rows, third bunch of rows, or what? J related to this first bunch of columns, the second bunch of columns, or what? The rows come in multiples of P's, the columns come in multiples of Q's. Okay, so I'm trying to take an I, J, and translate it into entries of matrix A and entries of matrix B. All right, before we get into it, here's the details, or here's the punchline. The IJ entry of the Chronicler product is, it's some element of A times some element of matrix B. It's this one, it says. So the goal is, how do I express in terms of I and J, and notice it's also got some P's and Q's in it, how do I express the IJ entry of the Chronicler product in terms of an entry of matrix A and an entry of matrix B, described in terms of row column for both of those. And apparently this is the answer. Okay, let's try to elaborate on that. All right, the ith row of the Chronicler product, I claim, involves A sub 1 plus I minus 1 divided by P, rounded down, comma K. I mean, the columns, whatever. I'm trying to talk about rows here. So here's what we're doing. We want to make that a little bit bigger. We want to see, for this given ith row of the Chronicler product, gee, how many elements of, or how many multiples of P have you gone through? Remember, we have P rows, P rows, P rows. So if I is between 1 and P, we're dealing with A sub 1, 1, if we're in this first column. When we're dealing with I, the row of the Chronicler product, between P plus 1 and 2P, and this first column, we're dealing with that. 2P plus 1 to 3P, we're dealing with A sub 3, 1, and so forth. So we're looking for a numerical way to determine that multiple of P that we're talking about. All right, so what we'll do is take that ith row, subtract 1, divide by P, then round that down. For example, if I is between 1 and P, I minus 1 is between 0 and P minus 1. You divide by P, that's P minus 1 divided by P. That's less than 1. Rounded down, rounds down to 0. You're getting A sub 1 something. So when I is between 1 and P, you're getting A sub 1 something. Like I said, you're getting something, depends on the column, but you're getting something along these rows here. Remember, what I've highlighted represents actually P rows in the Chronicler product. If P is between, let's see, we left off at, sorry, if I is between, P was the last one here, P plus 1 and 2P, we should be getting these out. Okay, suppose I is between P plus 1 and 2P. I want to look at this little parameter here. I equals P plus 1. We'd subtract 1, we get P. Divide by P, we get 1. Round it down, we get 1. Up through 2P. If I is 2P, we get 2P minus 1. Divided by P. That's P goes into 2P minus 1 one time with a, there's a remainder of P minus 1 over P. A remainder smaller than 1. So P goes in one time with a remainder smaller than 1. That remainder is chopped off, picks up the 1. We're looking at A sub 2 something. Right, A sub 2 something, that's right, isn't it? Yeah, A sub 2 something, that's what's highlighted here, and so forth. So we're using this rounding down function to determine from parameter I, describing a row in the Chronicler product, which of the A's we're going to use. And there's this division by P thing going on because B has P rows. So up there in that little picture, you see P rows at a time. What's up with B? This will involve also some row of B. Claim is the row of B would be I minus, so we've taken this I minus 1 over P parameter, I minus 1 over P, rounded it down, and multiplied by P. So what we're doing here is determining So let's look at this piece of information. So what we get with this is the remainder when I is divided by P, except when the remainder is 0. There's actually a typo in the book concerning this, in which case we get P out. So this is a way of producing the remainder when I is divided by P, except when the remainder is 0, then it produces a P. We want these descriptions, these parameters here, to range from 1 to NP. Right, we're dealing with the I values going in and the output being rows of B. So when I input any I between 1 and 2, 1 and n times P, put it through this process, it's going to output correspondingly a 1 through P. I can't simply use modular arithmetic because the indices start at 1, not at 0. I could explain all this in terms of mod arithmetic and just add 1. But then the notation is going to be really funky because adding 1, if I do it after the mod P, we're okay. If I do it before, it ain't going to work. But this rounding down allows you to take these 1 through NPs and peel off P at a time. So you're peeling off a 1 through P for this particular parameter here. We can treat the columns the same way, except now we'll describe it in terms of the J parameter, and it wasn't P columns we were worried about, it was Q columns. B had Q columns. So we effectively take what we had up here with the subscripts on the A's that involve P's and use subscripts now on the A's, but now for the column entry that involve Q's. So if you understand the first little part, then this is exactly the same kind of argument. So we've just swapped over to columns and we replaced the P's with Q's. In terms of the B's, what we're getting out is similar type stuff we had before. Here it is. Here's what we get out in terms of describing the entries of the B matrix. For the rows, okay, for the columns, we'll change the I's to J's and the P's to Q's. This is what we get out in terms of column entries of B. So, I'm pretty sure that wasn't very crystal clear, but all we're doing is trying to index the things properly because we're going to try to show something in a little while. And what we're going to show is going to require us to know where the entries of A are and where the entries of B are. But what we'll get by combining that information is, let me not shrink it just yet. The IJ entry of the Chronicler product is A sub, so we had this stuff, 1 plus I minus 1 over P rounded down, comma, 1 plus J minus 1 over Q rounded down. It's kind of a combination of these two. For the B matrices, it's based on kind of what's highlighted here. B sub I minus P times, picking up multiples of P here that are being subtracted off, should make sense. And the number of multiples of P you subtract off is, it's the same thing we had over here. I minus 1 over P rounded down, and then similarly for the J's. So here is how we express the IJ entry of a Chronicler product in terms of the entries of A and B, and in terms of the I's and the J's, and the dimensions of the matrices A and B, the P's and the Q's. Yeah, Gentle. I've made these notes out based on the first edition of Gentle. I don't know if he's fixed this in a second edition or not. I don't have a copy of the second edition, but it's out for a couple of years now. There's an error in Gentle's statement of this. He messes it up when P, or when I is a multiple of P and J is a multiple of Q. He's rounded down incorrectly, or maybe he did some modular arithmetic, but this is correct. So here's how we can relate entries of Chronicler products to entries of the matrices. We're going to use that shortly, so I'll label it with an asterisk. We'll just recall it at the time. Some properties of the Chronicler product. Okay, I take matrices A, B, C, and D. to be conformable for the addition and the regular whole matrix multiplication given below. The Chronicler multiplication, dimensions could be anything. But some of these involve, for example, here's some matrix addition. So make the dimensions correct so that the addition works and there's some regular matrix multiplication further down. All right, we get what they call associativity of scalar multiplication. You want to take a Chronicler product of A and B with scalar A on matrix A and scalar B on matrix B. Think how these Chronicler products are computed. Shouldn't be too surprising that you can put them scalars wherever you want. You can bring them outside of the Chronicler product. You can put them both on matrix A. You can put them both on matrix B. You can take one of them on A and one of them on B. You can interchange their roles even. Distribution of Chronicler product over regular vector addition. A plus B Chronicler product C is A Chronicler product C plus B Chronicler product C. Associativity. I don't know about you, but for me, this is not so intuitive that this Chronicler product thing is associative. Chronicler product of A and B, Chronicler product C, is the same as a Chronicler product of A with the Chronicler product of B with C. So we can move the parentheses around. Again, I don't think that's terribly obvious in the weird way that these Chronicler products are defined. Transposition property, this is possibly a little surprising. And the roles that A and B play are totally not symmetric. We ain't gonna have any commutativity for sure. The Chronicler product of A and B transposed is A transpose, Chronicler product B transpose. That's not clear. I mean, that's totally in violation to the way regular matrix products behave, but these Chronicler products are defined in a pretty different way. And finally, an interaction of Chronicler products with regular products, Cayley products, we briefly called it at the beginning. If we take the Chronicler product of matrix A and matrix B, Chronicler product of matrix C and matrix D, and then take a regular old matrix, row times column, matrix product of those, that's the same as the regular old product of A and C, Chronicler product with regular old product of B and D. The proof of this is left as exercise 3.6. And I'd expect some of these to be a little clunky, especially if you got to go back and refer to that asterisk equation. And we're going to use it here in a second. Another property, let A be an n by n matrix and B an m by m matrix, so they're both square matrices. The claim is the determinant of the Chronicler product. By the way, what are the dimensions of the Chronicler product? Is it really a square matrix? Yeah, it's nm by nm. Remember how the dimensions work? So it makes sense to talk determinants for these three. But the claim is the determinant of the Chronicler product is the determinant of A to the n power, that was the dimension of A, times the determinant of B to the m power. That was the dimension of matrix B. Now, I'm looking for something intuitive here. If I could relate the Chronicler products to regular products, I might have a chance of using something there where the exponents come from. Not too clear, might have some vague idea for one of them. But the author of our book states, the proof of this result, like many facts about determinants, is straightforward, but involves tedious manipulations of cofactors. All right. He said that before. And I've gone through and found other references. I like this Harville book, Matrix Theory from a Statistician's Perspective. And I've gone through and included more proofs than Gentle includes in his book for some of this stuff. I gotta agree with him this time. It'd take us a while to hack through that. I tried to write up some stuff and abandoned it. It's too long. It's 8 pages of Harville's book. So I agree, we'll take that as given. Property of Chronicler, determinants of Chronicler products. And let's do something a little more manageable. Let's show that the trace of the Chronicler product, remember trace was sum of the diagonal entries, is the product of the traces of A and B. Remember trace was the sum of the diagonal elements. All right, let's go through proof of that. This is where I'm going to need that asterisk equation. So we're trying to show for square matrices, A and B, n by n matrices, trace of the Chronicler product is a trace of A times a trace of B. Okay. That asterisk equation told us how to relate the entries of the Chronicler product of A and B to the entries of A and the entries of B. And it was this formula here with this rounding down stuff. So this is the same thing we had. We had P's and Q's, and this time they're square matrices. So I replace all the P's and Q's with n's in this equation. And this was good for I equals 1 to n squared. When I look at the Chronicler product, we'll have I ranging from 1 to n squared, and we'll have J ranging from 1 to n squared as well. N by n matrix, Chronicler product n by n matrix gives an n squared by n squared matrix. So this is the right range for the i's and for the j's. Okay. Suppose we take an I value in this set here. 1 plus k minus 1n plus 2 plus k minus 1n, blah, 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 up through k times n. All right, so here's what we've done. When k is 1, we're dealing with the first 1 through n I values. When k is 2, we're picking up at n plus 1, going to n plus 2, up through 2n. So this is pulling off these numbers 1 through n squared, n at a time. And that's what we were accomplishing with all this rounding down stuff that was given upstairs. But if we take I value from this range is from some multiple of n plus 1, this multiple of n plus 1. Add 1 to that, add 1 to that, add 1 to that, till you get to the next multiple of n. For example, n plus 1, n plus 2, up through 2n. 2n plus 1, 2n plus 2, up through 3n. So that's what we're saying here. If we look at, concentrating on these indices of A, 1 plus, rounding down I minus 1 over n, taking these I values here. So if you subtract 1, you're going to reduce these each by 1. For example, when we put this value in, you'll subtract 1, you'll be left with k minus 1 times n. Here you'll be left with 1 plus k minus 1 times n, 2 plus k minus 1 times n. Then we're going to divide that by n, where you're going to get a k minus 1 and then a little remainder term over here. And that remainder term is going to be less than 1. You're getting k minus 1 times n. Okay, divide by n, that'll leave you with a k minus 1 part and a little bit more. But the little bit more is less than 1. When you round down, the little bit more is gone. And that'll output simply a k minus 1. We got a k minus 1 times n divided by n, leaves you with a k minus 1. Plus a little bit more, but that was lost with the rounding down. So for such values of I, we get 1 plus, this rounded down, we get 1 plus k minus 1. We just get out k. So that tells you what's going to happen over that range of I values for these subscripts on the A's. And we ought to get, we ought to get A11, A11, A11 for quite a while. Yeah, in fact, this is the while when k equals 1. Looking over here at the indices on the B, we're looking along diagonal entries. Notice the subscripts on the A's and the B's are the same. This I minus n times I minus 1 over n, taking these values of I, well, we just saw this stuff in the bracketed quantity is going to be k minus 1. So this part reduces to a k minus 1, and we've got I minus n times k minus 1. Okay, you take these values of I, this is all being done under the umbrella of these values of I. We're going to subtract from those n times k minus 1. So here we've got 1 plus n times k minus 1. Subtract k minus 1, you lose that stuff and you keep the 1. This one, you lose that stuff, you keep the 2. And so forth. This will output, this equation will output for those values of I 1 through n, as they ought to. We're trying to get 1 through n indices on B sub. Remember, B is n by n. So we're trying to get 1 through n out of this, and we're also trying to get a 1 through n out of both of them, actually. All right, so we are outputting the right places for these things. So when we look at this bunch of I values, we can rewrite that thing we get out of the asterisk equation as we're getting k's out for the subscripts on the A, so we get A sub kk. On the B's, we're getting I minus n times k minus 1. We're getting that stuff out. Well, at least they're definitely diagonal entries. The diagonal entries of the Chronicler product involve a diagonal entry of A times a diagonal entry of B. That should be not a surprise if you think about the partition picture of the matrix. Okay, so if we look at the trace of the Chronicler product, that was the hard part there. Trace of the Chronicler product would be the sum from I equals 1 to n squared of all these diagonal entries. Okay, but when we take I between 1 and n squared, so we started the thing, we can break that down into these various little ranges here. When k equals 1, we had I ranging from 1 to n. When k equals 2, we had I ranging from n plus 1 to 2n, and so forth. So we can sum from 1 to n over the k values these things here. 1 plus k minus 1 over n. 1 plus k minus 1, times n. And then we end at k times n. All right, so all we've done is break this summation into a sum of sums. We had the indices on the A's to be equal to k, so we made the substitution there in terms of the k. So when you go through k equals 1, you get A11 times B something, A11 times B something else, A11 times B something else. Yeah, you get that A11 a whole bunch of times. And you're moving along the diagonal of matrix B, it looks like. The indices of row and column entry indexes are the same. All right, well, now all we got to do is cleverly re-index. Let's take this I parameter. You know, as far as the A's are concerned, I could bring the A sub kk outside. In terms of the I's, let's re-index that. We've got I ranging from 1 plus k minus 1 to n up to kn. Okay, so that's a range of n numbers. Let's subtract off this k minus 1 times n thing. And let's start at I equals 1. And then we'll end up at n. Yeah, we'll end up at n. I need to deal with this, so what I'm doing then is saying, hey, if I plug in I equals this right there in that index, you're going to subtract off an n times k minus 1. You know, you're going to lose this n times k minus 1 term. And the B is going to get A sub 1, 1 when we start at I equals 1. So I'm going to shift the indices. What that'll allow us to do is start at I equals 1, eliminate the k minus 1 times n stuff, eliminate it here and here as well, keep the same range, that would be 1 to n, 1 to n, and get the B sub i's. So we've shifted the index on the i's by reducing by k minus 1 times n here. That effectively drops these subtractions here, leaves us with a B sub I, a manageable range on the i's of 1 to n, and that's the trace of B. So we get a sum from k equals 1 to n of A sub kk, 1 to n along the diagonal, that's the trace of A. I equals 1 to n, B sub I along the diagonal, that's the trace of B. This might not be too surprising if you were to write out a small example in terms of how you take Chronicler products. What's really nightmarish in it is all this rounding down stuff to translate entries of the Chronicler product into entries of A and entries of B. But once that's accomplished, then it's just a change of indices, a shifting of indices to produce the result. Okay, so trace of the Chronicler product is the product of the traces. Let's define an inner product on matrices. Okay, I can't say I've ever seen this done before. The story's going to fall a little flat, I think. We're going to take matrices A and B to be n by m matrices. So A and B are the same size. Need not be square though. Let the columns of A be the vectors A1 through A sub n. Let the columns of B be vectors B1 through B sub m. All right, so we've done this before where we've described the column vectors of a matrix by giving them, single subscripts, first column, second column, and so forth. Same thing with matrix B. Define the inner product, or maybe the dot product, of matrix A and matrix B as follows. It's a scalar, denoted the same way we denoted inner products for vectors. We're going to define it as sum from j equals 1 to m A sub j transpose times B sub j. Let's see, these were columns of A transposed. So they still be the columns of A, but written as a row vector. And then we're multiplying them times these column vectors. This is a row times column type product. It's the jth row of A times dotted with the jth column of B. Did I say that wrong? I did say that wrong. The jth column of A dotted with the jth column of B. It's a dot product, an inner product of corresponding columns. So we could write that in terms of vectors as the inner product of A sub j with B sub j, where A sub j and B sub j are these column vectors. What you've really done is you've multiplied every element of A by the corresponding element of B, entry of B, and added them all up. So you've really treated matrix A almost as if it were a really long vector instead of a matrix. And same thing with vector B. You've multiplied corresponding entries together and added them up as if they were big long vectors instead of arrays, instead of square or n by m matrices. But you've really just multiplied corresponding entries together and summed them up. That's accomplished in terms of this introducing the matrices. The little transpose deal here is another way to write dot product of vectors. Since we used a matrix product in there, that little transpose thing, technically we're getting out one by one matrices, but we're treating them as scalars. If A and B are themselves just vectors, m by 1, say, so we treat them as column vectors, then this is just the regular old inner product we had before on vectors. Some properties. Okay, this should be straightforward stuff because we're really just rehashing properties of vector inner products with a slightly different notation. Some properties of inner product of matrices. All right, take A, B, and C to be matrices. Where you can do whatever addition and multiplication is required in the following. Then the claim is, if A is not the zero matrix, then the inner product of matrix A with itself is greater than 0, it's positive. For the zero matrix, inner product with everything equals 0. The inner product of 0 with itself equals 0. There's a commutivity here, just like there is with the regular inner product for vectors. That is, inner product of A and B is the same as the inner product of B and A. If we take a scalar and put it in that inner product, we can put it on the first component, the second component, or bring it outside. If we've got a vector sum in the first component, we get a usual type addition behavior with the inner product. If we had addition in the second component, we get the usual type addition behavior there. Here's something new. There's a couple of things new. The inner product of A and B equals the trace of A transpose times B. We never mentioned that in the past when we were doing inner products of vectors. I don't think we talked about trace in the setting of vectors. The inner product of A and B is the same as the inner product of A transpose and B transpose. If you think how these are computed, that's not much of a surprise. And Schwarz's inequality. the absolute value of the inner product of A and B is less than or equal to the square root of the inner product of A with itself times the square root of the inner product of B with itself. And if you're thinking about it the right way, you should desperately want to put a geometric interpretation on that. This probably ain't the setting for it. The setting for it is R2 or maybe R3. But this is the same type of Schwartz inequality we had for vectors. Let's look at some of those. Good news, these are not long proofs. Okay, so let's go through and prove some of those, a couple of them. I guess 5 and 7 are left as exercises. So let's look at the rest of them. Okay, first one, this claim about inner products being positive or 0 is given. Okay, let the columns of matrix A be A1 through A sub m, like we were doing. If A is not the 0 matrix, then one of those columns must have a positive norm. If they're all norm 0, then you got the 0 matrix. We don't have the 0 matrix. One of them has a norm greater than 0. So if we take the inner product of A with itself, here's that definition in terms of, ultimately in terms of dot products, if you like. So we're taking the dot product of column vector J of matrix A with itself. We said one of those columns is not the 0 vector. Okay, what we get when we do the inner product of a vector with itself is the norm squared of that vector. Okay, well that's going to be greater than or equal to sum over all the columns. It's going to be greater than or equal to this particular column. That particular column was where we had a non-zero vector. So we know that norm is greater than 0. And there you go. If A is non-zero, inner product of A with itself must be positive. That's this claim. Secondly, take a matrix of zeros. Then the columns are all 0 vectors, say 0, 1 through 0 sub m. The inner product of A with 0, by the definition, is this type thing. If you like, I could write it in terms directly of an inner product. These are indirectly inner products. You do that multiplication. Hey, you got nothing but zeros in this second matrix. You're going to get 0 out. We could write that, if you like, as a sum of 0 sub j transpose. Just putting the zeros in a different place. You do this computation. You got all zeros in this first one. You're going to get zeros out. And that is, by definition, the inner product of 0 with A. The inner product of 0 with itself, of course, is 0. Okay, a symmetry type behavior. Inner product of AB equals the inner product of B with A. True because we have real vectors. If we had complex scalars and vectors with complex entries, it would be more involved. This wouldn't be true in general, but it is in the real setting. All right, let the columns be, subscripted A's and subscripted B's. Then when we compute the inner product of A and B, we do so like this by definition, which can be written in terms of inner products here. All right, here we're doing regular old vector inner products. Why, we established, I guess it was theorem 2.1.6 part 2, you can change the order when you're dealing with the vectors. So we are dealing with vectors, or column vectors. We're adding a bunch of them up, but we can swap the orders there to get the inner product of B sub j with A sub j. That inner product can be written as a matrix product using transposes. Think what you get. We've taken this column vector, B sub j, now by transposing it, written it as a row vector, multiply it by a column vector using the matrix product type stuff. And that produces the inner product that we've done before. And that's, in our new setting, that's the inner product of B with A. So inner product of A and B equals inner product of B and A. The thing about scalars, okay, let's take those column vectors to be the usual thing for matrix A, then the column vectors of S times matrix A, well, it's just that scalar S times each of those columns. So if we take the inner product of SA with B, we'll get that jth column of SA, transpose, times B sub j, all right? Scalar times the transpose is the same as, well, the transpose of scalar times vector is the same as scalar times the transpose vector. Of course, you can pull that scalar outside of the transposing. Now we've got this parameter S on all of those terms, bring it out front, distribution. And what you're left with, A sub j transpose B, well, that's the inner product of A and B. So we've actually claimed a couple of equalities here. Here's the first one equals the second one. Now let's establish the next one, piece of cake. Let's take A times SB. You know, you can swap things around, get the scalar S in the first entry. And we just showed when you got it in the first entry, you can pull it out front. Pull it out front, swap them back. So there's a little shortcut on this. We'll do another one where we take a shortcut when it involves this changing orders on the inner products stuff, like it does here. A plus B, inner product C, okay. Let the A's, B's, and C's be the columns, as we have done many a time. The columns of A plus B is matrices, or A1 plus B1, A2 plus B2, you know the story. So if we write the inner product of A plus B with C out, we'll get transpose of the columns of the first one times columns of the second one. Transpose of the sum is the sum of the transposes. We stated that as a property of transposes somewhere along the way. I didn't document it here though. Distribute. Okay, do the distribution that you can do with this type of multiplication. And here we've got A sub j transpose, C sub j. Let's pull that off. That's the inner product of A with C, inner product of A with C. Over here, treat that as a single sum, inner product of B with C, and that was the claim. So we can do that kind of a sort of distribution type thing. Probably the appropriate thing to call it is a linearity. It's a linear in the first entry. What about linearity in the second entry? Let's do that same little trick. We'll start with C, inner product with A plus B, swap the orders. Part 2 says you can reverse the orders and not change the inner product. We know when we've got addition in the first component, we can break it up like this. We just showed that. Swap the orders back on those constituent parts, moving things back to the correct side, and that establishes the other claim. Inner product of C with A plus B, inner product of C with A plus inner product with C with B. Inner product of A and B equals the inner product of A transpose with B transpose. Okay, good news is it's one slide. Let me do my thing. I say this is my notation of indicating the entries of the transpose with a superscript of T. So A transpose has entries A sub ij super T, B transpose, you know, similar type thing. I know the relationship that super T just means swap the indices to go back to the original matrix in both cases. Okay. Denote the columns of A with, you know, A sub j's and B sub j's for the columns of B. Owen with the superscripts of T for the transposes. So I need all that stuff just to talk about these quantities. Inner product of A and B, by definition, it's this. All right, here, A sub j transpose times B sub j, that's a little inner product itself. What we're gonna do is run along the components of A sub j, multiply them by corresponding components of B sub j, and add. Let's use a first index to indicate the components, and that's where they came from because they're column vectors. So for A sub j transpose, we'll get the entries A sub 1j and then A sub 2j and so forth. Here we'll get B sub 1j, B sub 2j, and so forth. We'll multiply corresponding pieces together and sum them up. They come out of the matrices with the i's in the first position. This transpose here has really nothing to do with the transpose of matrix A. This transpose here was so that we could multiply that column vector times that column vector. Well, you can't multiply column vectors. You can multiply row vectors by column vectors in this order. And then that's what the transpose accomplishes there. So that's what that T is for, looking in this direction. All right, so we get this summation, I equals 1 to n. Of these entries from A and B. Let's interchange the i's and the j's. So the ij becomes a ji in both cases. Let's interchange the roles of summation, right? See what little arithmetic has been done. So sum over the j's first and the i's second, commutativity, so nothing there. Now where are we going here? We're trying to get to transposes. So somewhere along the lines, I need to get rid of the a's and the b's and get some a super t's and b super t's. Let's do it now. Let's change the a sub ji's into super t's. So that'd be a sub ij super t, b sub ji, b sub ij super t. All right. This is exactly a sub j super t transpose times b sub j super t. For the same reason, we could expand this without the super t's as this. So we're doing that same type thing that we did upstairs, except now we've got the super t's involved. Hey, and once you get it in that form, this is, by definition, the inner product of A transpose with B transpose. It's the jth column of A transpose, transposed, times the jth column of B transpose. All right, so I said transpose 3 times, once for the A transpose, once for the B transpose. Those are kind of the important ones, and once to make that product exist. But this is, by definition, what A transpose inner product with B transpose is. All right, any more of those? That takes care of the proofs from this section. This is a more reasonably linked section, really, than that previous one. All right. This thing we've defined as an inner product on these matrices, it really is an inner product. On a vector space, we require an inner product to satisfy certain properties. This shows that this one does. This Schwarz's inequality, you always use Schwarz's inequality to prove a triangle inequality. So this Schwarz's inequality guarantees that you can make a norm induced by that inner product to find the norm of vector A. You take the inner product of A with itself, square root of, as long as you're in the real setting. So what we've got then actually is a vector space with a norm and an inner product on it. The vector space is it's really isomorphic to Rnm. All we've done is taken matrices and treated them almost as if they were vectors. The new stuff would be arguably in terms of this transpose deal and this trace stuff. The rest of it's the same kind of thing we did with vectors. If we've got inner products, then we can talk about orthogonal matrices. Two n by m matrices, A and B, are orthogonal if their inner product is 0, the 0 scalar. A set of matrices, n by m, is orthonormal if they're pairwise orthogonal and the inner product of one with itself is 1, so they're norm 1, and they're pairwise perpendicular, pairwise orthogonal, usual definition of orthonormal. And one reason we can do all of this stuff is we're just dragging the behavior of inner products on vector spaces into something totally similar in this setting of matrices. We could talk about orthonormal bases. We could do the Graham-Schmidt process. We could do projections. If we can do this stuff with inner products, we can do all those things we did with inner products in the setting of vector spaces. We've made a vector space where the vectors are matrices in a rather uncreative way, in fact. All right, a little history to wrap this up. This is pertinent to us because this is theory of matrices. The term matrix was used for the first time by this guy, James Joseph Sylvester, in 1850. So the term matrix comes around in the 1850s. Now this term doesn't come from antiquity. It's really Arthur Cayley. And remember we called the matrix product the Cayley product. I think it was the first page of this section of notes. Said there'd be a reason for that later. It's Sylvester that brings the term matrix. It's Cayley that brings the theory. Arthur Cayley was the first to concentrate on matrices themselves and the first to publish articles on the properties of matrices. For this reason, Cayley is credited as the creator of the theory of matrices. Here's a reference I don't think I've mentioned in these notes before. Mathematical thought from ancient to modern times. It's a little dated these days, but it covers the history of math quite thoroughly up well into the 20th century. A lot of history of math stuff kind of runs out of gas in the 19th century, but this covers a lot of the 20th century stuff. It's classical reference on history of math. Cayley introduces matrices to simplify the notation and the study of invariance under linear transformations. Something from 1855. If you like reading stuff in French, there's a copy online. In 1858, he published a memoir on the theory of matrices. You can find a copy of that. It's published by the London Philosophical, the Royal Society of London Philosophical Transactions. It's in English. So there's a link to that in the notes. And in this paper, Cayley defines a sum and the product of matrices. That's why the way you multiply matrices was referred to as a Cayley product when we first introduced it. It's a nice homage to the history of these ideas, but we'll probably just call it a product of matrices from now on, as before. And a product of a matrix times a scalar. So he's introduced this linear combinations idea, along with the idea of a product of matrices. So this stuff dates from 1858. We put our fingers on the precise date. He introduces the identity matrix, the inverse of the square matrix, showed how to find inverse matrices, and how they can be used to solve systems of equations. So that's sophomore linear algebra. So, and I can put my hands on the first publication that basically introduces sophomore linear algebra, at least from a perspective of matrices. I'd say what's missing is, hey, where's the vector spaces? And we mentioned a historical reference about vector spaces, I think at the end of the last section. So there we go with matrix multiplication, some new variations on how to multiply matrices, Chronicler products, inner products with or outer products with the vectors. So that takes care of this section, and we'll move on to section 3.3. Bye-bye.